Hello, this is Tom Hobbs, and this is the second in our series of 4 videos on Bayesian methods and approaches for synthesis of ecological data. And the topic of this lecture is moment matching, which turns out to be an incredibly useful technique that's not widely taught. I've never seen it in a text, but it turns out to be very useful for forming priors on distributions using published literature. Okay, the overarching objective of these videos is for us to learn Bayesian methods for synthesizing existing data and published findings to enhance our insight in ecological research. In the first video, we reviewed the components of Bayesian inference, the components of Bayes' theorem, both mathematically and graphically. I made a bit of a case for why we should always strive to use informed priors when we can. And I then brought up a problem using published means and standard deviations. And it's the intent of this video, video number 2, to show how to solve that problem. So slides for this lecture and all of the others can be found at my GitHub site. And you may want to pause and write this down. I think it would be quite wise for you to have these notes in front of you as you're going through the video, such that you can take notes and so on directly on the slides. So the slides can be found there. Okay, here's the problem. All distributions, all statistical distributions have parameters: negative binomial, Poisson, multinomial, binomial, gamma, log normal, Weibull, normal. All of these distributions have parameters. So in this case, we're looking at a probability density function for the random variable z. And what we have is the probability density of z conditional on 2 parameters. And those parameters, for the most part, control the shape and the dispersion of that PDF. However, here's the problem. The normal and the Poisson, out of all of the distributions that we could potentially use to represent ecological processes, the normal and the Poisson are the only distributions out of dozens for which the parameters of the distribution are the mean and the variance. The parameters of all other distributions, all but the normal and the Poisson, are functions of the mean and the variance. But what do we usually get from the literature? Well, means and standard deviations or standard errors, sometimes variances. And so how can we put these values that we get from the literature to use in composing reliable, informed priors? The trick is called moment matching. It's a quite simple technique, as I said, not widely taught. So let's say we seek a prior on the parameter mu using published data on some mean, using published data x bar and sigma squared. And we're seeking a prior that's not for the normal or the Poisson distribution. So we need numeric values for the parameters for the distribution of mu. And how do we find those? So we know that alpha is a function, f1, of the published mean and variance, and beta is also a function of the published mean and variance, f2. So it follows that mu is distributed as alpha beta, where alpha and beta are numeric values that we compute from 1 and 2. Now, this is the general theory. Why don't we take a look at an example, and I think it will bring it home how moment matching works. So we're going to moment match the gamma distribution for a non-negative continuous quantity, something like above ground net primary production. It can take on real values from 0 to infinity. The mean of the gamma distribution is the ratio of the first and second parameters, alpha and beta, the rate and the shape. And the variance is alpha over beta squared. So the question is, if we're going to compose a gamma prior, we need to know alpha and beta in terms of mu and sigma squared, so that we can use values from the literature to form that prior. So here's this, all we do is solve two equations and two unknowns. Here by substitution, so mu is equal to alpha over beta, sigma squared is equal to alpha over beta squared. We solve one for beta and substitute beta in two. We then solve alpha and substitute the solution for alpha in two, and then solve for beta. We now have an expression for alpha and beta in terms of the mean and the variance of the distribution, and that enables us to use published tabulated values to form a prior on mu. So here's an example using above ground net primary production and sagebrush step, a non-negative real number. So the mean was 36.7, and the standard error, that is the standard deviation of the distribution of the sample mean, was 1.97. So the distribution of mu is then alpha squared over beta squared, comma, alpha over beta squared. So that's 36.7 over 36.7 squared over 1.97 squared, and then 36.7 over 1.97 squared, which if we do the math, do the arithmetic actually, we have mu is distributed as 347.1 and 9.6. And there's this corresponding JAGS code. I recommend that you look these up every time you use them, at least to start, because it's so easy to make a mistake here. You need a set of, a tabulated set of moment-matched parameters for the various distributions, and I'll show you later in the video where you can find those. Here's another example. This is a bit more complex, but we do the same thing. So moment matching the beta distribution for proportions. The beta distribution gives us the probability density of random variables with support on 0, 1. So something like the probability of survival. Can't be less than 0, can't be greater than 1. Doing the same math of solving two equations and two unknowns. We have mu is the mean of the beta distribution is alpha over alpha plus beta, and the variance is alpha beta over alpha plus beta squared, alpha plus quantity, alpha plus beta 1 plus 1. If we solve those two equations in the two unknowns, alpha and beta, we get expressions for the first and second parameters of the first parameter alpha, the second parameter beta, of a beta distribution in terms of the mean and the variance, which again is going to enable us to use published values on means and standard deviations or variances to compose priors on beta distributed variables. So it's best in this case that you write functions that you tuck away somewhere. These are functions in R. They can easily be translated to JAGs if you need to, but these are impossible to memorize. I wouldn't try to do this. So write some functions, test them, and put them in a place where you know you can find them, and you'll always be able to moment match the beta distribution. So another example. This is the annual survival probability of adult female bison on the northern range in Yellowstone. So it's because it's a survival probability, it's a 0, 1 continuous real number. The mean was 0.89 with a standard error of 0.023. So we can use the moment matched function to find values for alpha and beta, and then we can use those values to compose our informed prior on survival probability of adult female bison. And here's the JAGS code. It's a simple translation of the math, almost one-to-one. There are several good sources of information for functions of moments to compute parameters. So where we have the parameters in terms of the moments, you can get the moments in terms of the parameters in almost any stat book, any Bayesian stat book, any stat book really, or on Wikipedia. But the other way, where we find parameters in terms of the moments, is not widely available. You can find it in our textbook, my textbook with Mevin Houghton, Bayesian Models, a Statistical Primer for Ecologists. It's in one of the appendices. Mick McCarthy has a similar table in his very fine book, Bayesian Methods for Ecology. And then on the GitHub website that I showed you earlier, there is what I call a distribution cheat sheet. It's a two-sided sheet that gives a lot of the pertinent information, useful information on a toolbox of statistical distributions that are widely used to solve ecological problems. Okay, the take-home message from this video is that prior distributions are powerful tools for synthesizing results from ecological studies. They allow us to benefit from hard-won published data, but using them reliably requires that we choose distributions with proper support, and those may not be distributions like the normal and the Poisson. Moment matching is the tool that we use to enable us to use published means and standard deviations to find parameters of distributions for which parameters and moments are not the same. Thanks very much, and we will move on to the next video shortly.